Well, welcome to the Physics Lounge. We're taking a look at the 2022 Level 3 Physics Waves paper. So Jane enjoys playing the guitar. When Jane plucks the string, one of the resonant harmonics that's produced is shown in the diagram below. State which harmonic or overtone is shown in the diagram above and label at least one node and one antinode on the diagram. So this is a guitar string. It's fixed at both ends. Your fundamental frequency would be one of these humps, not three. So this is the third harmonic, or the second overtone. And so we've got antinode, node, antinode, back to front there. Node, antinode, node, antinode, node, antinode, node. Now the assumption is that we're dealing with displacement nodes and antinodes, not pressure nodes and antinodes. Which is a fair assumption because that's your typical, unless they specifically mention pressure. The length of the guitar string is 0.645 meters. The frequency of the harmonic indicated in the diagram above is 995 hertz. Calculate the speed of sound through the string. So the wavelength you can see is 2/3 of that length. So 2/3 of 0.645 gives you the wavelength. You've got the frequency given to you there, 995 hertz. So we're dealing with a V equals F lambda to find the speed of sound through the string. So the frequency 995 times whatever this part works out to be. I'm not going to go through the calculation, you can do that yourself. A little bit unusual. Calculating the speed of sound through the string, because typically we're interested in the speed of sound in the air. Okay, so that gives us something a little bit weird in our heads to work through, but because it's a relatively simple question, you can just plug through with this. That's always the best approach if something seems a little bit amiss. Sometimes examiners make small errors or have little inconsistencies that upset the apple cart a tiny bit. But that's okay, you can work through that one there. While Jane is playing the note of 995 hertz on her guitar, her friend Mele tunes her guitar by playing the same note, tunes her guitar by playing the same note as Jane, same loudness, excuse me, at the same time. They hear beats of 5 hertz beats, which means she's either going to be 990 or 1000 hertz. So Millie tightens her guitar string so that sound travels faster in the string until beats are no longer heard. So the sound travels faster in the string. State Millie's original frequency. Explain the effect tightening the string has on the frequency of the note that Millie was producing on her guitar. Okay, so I'm going to do it this way. Start with this. So when you tighten the string, the velocity increases. And then from V equals F lambda, if you increase the velocity for the same wavelength, remember the length of the string can't change, that means the frequency has to increase. So by tightening the string, you see an increase in frequency. If you see an increase in frequency to match the frequency, then it must have been at 990, that was the original frequency. Okay, that's generally the gist of how the question's going to go. There was a previous question that actually had, in a previous exam, that actually had an equation that showed how this works, but the general phenomenon is that if you increase the tension by tightening the string, you're going to increase the speed that will pass through. Maybe a little bit unkind expecting you to have to remember that, but yeah, it is what it is. D, Jane also plays the flute, which can be modelled as an open pipe. So remember, open pipe means it's open at both ends. Mele plays the clarinet, which can be modelled as a pipe which is closed at one end and open at the other. So that's the clarinet, that's the flute. Explain why Mele, so Mele was playing the clarinet, and Jane was playing the flute. So explain why Mele cannot produce the second harmonic on the clarinet whereas Jan is able to produce the second harmonic on her flute. So you can illustrate by drawing diagrams. With the open at both ends, your fundamental is going to look like that, and then your second harmonic is just going to introduce another node-antinode pair. So whereas we've got antinode, node, antinode, you're going to have antinode, node, antinode, node, antinode. So you've introduced another node-antinode pair in between there. So that's going to look something like that. I'm terrible at drawing these diagrams. So that's what the second harmonic will look like on the flute because of the positions of nodes and antinodes. If you increase it for so that's for the flute. Let's just going to do that, flute. If we do the same thing for a clarinet, so clarinet, the fundamental being a node and then an antinode, a node at the closed end, that's going to be zero displacement, therefore an a node. There's the first harmonic. The second harmonic would have to have node, antinode, node, antinode, which, let's see, antinode, node, antinode, node. And what goes on there, that is a tripling in the, oh, hang on, something I've done wrong here. No, I haven't. But that is effectively a tripling of the length of the wave rather than a doubling. So this one, going from here to here, that's times 2 the, well, it's actually halving the wavelength, but you're doubling how much of the wave you can put into the pipe. And then same thing down here, you're adding a node and antinode, but you're not doubling the length, you're actually tripling. So you've had to include another 2 sections. I'm running short of colours and things here. So this was your original section here, and node antinode, and then by adding another node antinode pair, you add basically 2 additional sections. So that's not possible in terms of doubling, which would produce you, or doubling the amount of wave in the pipe, or halving the wavelength. Halving the wavelength would only add that other half there, and you can't have that on an open pipe. The open end would have to be a closed end and produce just a node. So that's the issue that's going on there. So you're effectively 1/3 going from here down to here, 1/3 of the wavelength, which would be the third harmonic. That's the issue, why you can't do that. So if you're explaining this, you'd need to explain the positions of nodes and antinodes, which are governed by the open and the closed ends. Open and open allows for a symmetrical wave, closed and open allows only for an asymmetrical wave with that quarter wavelength, and then you just can't double it. All right, we'll take a pause and then we'll come back for question 2. Okay, well, I had a little pause. I'm not sure if you had a little pause, but we'll carry on. So question 2 on waves, level 3. Vincent is studying interference patterns formed by diffraction gratings. Here's a set of diffraction gratings with different slit spacings. Vincent shines a red laser through the gratings and observes the pattern formed on a screen that is some distance away. So you're very classic setup. There's no unusual context at all here. We're just shining a laser through diffraction gratings onto a screen. Describe the effect on the pattern of fringes that are formed on the screen when the distance d between slits increases. The width of the slits remains the same. Okay, diffraction grating. So you have quite a wide spread of your if there's a diffraction grating, here's our laser coming in. We have quite a wide spacing of fringes with your 0th one in the middle. Really difficult to draw, but this just to make it jog your memory there. So a wide spacing means you're going to use n lambda equals d sine theta for your consideration. You can't use n lambda equals dx over L because that relies on a small angle of spacing. So small angle is where sine theta is approximately, no, that's for the other one. The tan theta is approximately equal to x over L. Yeah, something like that. My brain's not working totally wonderfully first thing in the morning here. We've got a new cat. Anyway, describe the effect on the pattern of fringes that are formed on the screen when the distance increases. So the distance is increasing. The wavelength stays the same. If we consider, say, it's no point considering the central 0th fringe, but if you consider any of the other ones, first or second or third, whichever one you choose, it's staying the same. So for an increase in d, in the distance between the slits, for the same n and lambda, you're going to have to see a decrease in the sine theta portion. So you're going to see a narrowing because theta is going to decrease for sine theta decreasing, which means you're going to see those fringes coming in to get you a smaller d. So the effect on the pattern of fringes, they will come closer together. B, Vincent uses the diffraction grating to study blue light from the new laser. Okay, so we've changed the colour of light. He uses a grating with 6.00 times 10 to the 5 lines per metre. So notice we've changed from D to N. So N equals 6.00 times 10 to the 5 lines per metre. Important to take note that it's lines per metre, not lines per millimetre, so that allows you for an easy conversion between N and D. He sees, and we don't know how many lines per metre the initial two gratings were, so we could just have to assume this is a brand new one. He sees a series of bright dots that are the maxima, measures an angle of 54 degrees between the third bright dot and the central, so that's n equals 3. There's our theta, that's our n. Calculate the frequency of light that he is observing. Okay, so let's just take a little look at our n lambda equals d sine theta. So I'm not going to do the calculations, but I'll show you how you'd work this through. So we've got, and I'm going to have to go to a smaller dot size because we're sort of running a little bit lower on space, but we're dealing with an n equals 3. We're dealing with a lambda that we're trying to find. Once we find lambda, we're going to use v equals f lambda to find the frequency. So we'll know lambda at the end of this. We're trying to find the frequency, and the velocity is the speed of light, 3.00 times 10 to the 8 meters per second. D is going to be 1 over n that we were given, and theta we were given with the 54 degrees. So we basically rearrange that for lambda and then plug that lambda value into this over here. And that should give us a frequency. C, Vincent next shines white light through the same diffraction grating of n lines per metre. He notices the central antinodal line is white and each of the orders produces a complete spectrum. Explain both observations using a knowledge of colours and wavelengths of light. Okay, so you're probably going to have to refer back to n lambda equals d sine theta here, and you're going to say for each fringe, this is first explaining why a spectrum is produced. So why is a spectrum produced? Because you've got, for the same n value, the same d value, you're going to have, say, an increased or a decreased wavelength, and therefore an increased or decreased angle of spread. So a larger wavelength will see a larger angle of spread. So you'll see the longer wavelengths, such as red, going to a higher angle of spread, so they'll spread further, and blue will have a lower spread. So you're expected to kind of realise that the blue will be closer to the central fringe. Why is there white at the middle? That's the other thing that they want you to know. It's because the angle is 0 for all of those in the central bright fringe or antinodal line, as they talk about. So that has the effect of combining all of the wavelengths together. The equation basically doesn't work for there because there's no, I suppose it does work. I mean, what's sine of 0 is 0, but that just means you have 0 on the right hand side. I suppose it doesn't work then, because n and lambda, well, n is 0, so there you go, 0 times 0 equals 0. Okay, a little bit silly. But the equation doesn't help you so much in your qualitative understanding, whereas normally equations give you hints towards the qualitative understanding at least. In this case, you have to recognise that you're combining all of the wavelengths of that central fringe, because there's no diffraction directly in the centre. So there's no spreading out according to wavelength. Okay. D, while studying the effect of shining white light through the diffraction grating, Vincent carefully measures an angle of 28.05 degrees for the violet light from the central bright fringe. Okay, so that's violet light, so red's going to be a greater angle. He then measures an angle of, oh, there you go, 50.82 for the red light of the same order. So do we know what order this is? I don't know. So you've got the difference between the red and the violet light there, which is 254 nanometers, just to put it in terms you might be more familiar with. That's the wavelength difference. And they've got a nice diagram here to kind of show what's going on. Although they do have it spreading out in 3, like a circular kind of, kind of angle here implied, whereas you're probably used to a straight heading onto a screen. In actual fact, they are spreading out in that kind of two-dimensional circle pattern, but and a curved screen would give the most accurate of what's going on. Anyway, so it says calculate the wavelength of the red light, and begin your answer by identifying what is common to both red light and violet light in the equation n lambda equals d sine theta. So what's common is clearly d. So d is going to be the same for both. And what else is going to be the same for both is n. Now, I suspect this is expecting a simultaneous solving, which is a little bit mean. It's a little bit outside the usual. So let's just, for the sake of anything, it doesn't matter which one it is, but make n equals 1 for both of them. And then d is, you know what, it doesn't even matter, because what we do know is from this little bit here that wavelength of red minus the wavelength of violet is equal to that. So you can rearrange this equation, n lambda equals d sine theta, for, it actually, through the diffraction ratio, so we might know d from up here. It's a little bit of a, you don't really need it. There you go, 6.00 times 10 to the 5. I'll just put it there for the, that was n though anyway, so n equals 1 over d, d equals 6.00 times 10 to the 5 meters. Sorry, I've done that back to front. That's what n equals, and then you calculate, and that's lines per meter. I'll just double check that. I know there's a little bit of a sidetrack, it is lines per meter. A little bit of a sidetrack because the things that are common to both you can cancel. So if n is both 1 for each of those, for the violet light and for the red light, then you can do, you can effectively eliminate that from the equation, subtract one equation from the other in the same way. So d sine theta minus d sine theta, which looks silly, but remember it's a different d. You've got a d for the red and a d for the violet. I keep saying blue, I think, I'm not sure, but anyway. And you've got the two at the two angles, so what was it, sine of 58.2, so I'll just kind of highlight that and throw it down there, highlight that, throw it down there, and that should equal that 2.54 times 10 to the minus 7, which I'm running off the edge of the page a little bit there. So where does that leave us? Well, if n equals 1, then this part equals the wavelength of the red. And so you can rearrange your calculation, because we know the d value, we know the sine value. We can, it seems to me there's another way of doing this as well. This is sort of fluffing around just a little bit with a slightly awkward excellence question. But if you rearrange so that you have the wavelength of red equaling d sine theta over n, so d red over sine theta red over n red, but n's going to be the same, doesn't matter what it is. You do the same for violet, so wavelength of violet equals d red, which is the same again. Let's just kind of cancel that out. Where are we? Sine theta violet over n. So those two are the same. If you are got myself into a bit of a tiz here. Yeah, so I suspect, okay. Then if we just plug all the values that we know into these equations, we can find let me just see if I can represent this here. You'll end up with a number on the top. So we do use the conversion for n and d and stuff to find d. We know theta, excuse me, for the red. So we'll end up with wavelength of red equals some number over n. Wavelength of violet equals some number over violet, because again we've got both of those. So we now have an equation that we can make in the subject, and which will be whatever that number is circled up here divided by the wavelength red. So I'll just do that over that. And the same for violet. It'll be n equals whatever is circled divided by the wavelength for violet. We can equate those. Those two should be the same because they're both equal to n, and it's the same n value that we've used. So we can make that equal to that. And then now we have two equations with two unknowns that we can solve simultaneously. So we've got this equation here, which has the two unknowns of wavelength red and wavelength violet. And here we've got our equation which has the same thing, two numbers but two unknowns. And then you can simultaneously solve them. I won't get into how you do that, but you can either do it by substitution, which is probably the easiest. Just rearrange to make, say, lambda violet, because we're trying to find the red light. So if we find a value for lambda violet and substitute that in. Very awkward. In some ways, I don't think that's a particularly useful question for level 3 physics, because it's not really assessing your physics knowledge in order to do this. It's assessing your maths knowledge. But, you get what you get, and you just do the best you can. Okay, so Doppler effect, question 3. Two police cars I've got the speed of sound in air, 340 meters per second. Two police cars have identical sirens of frequency 7.50. This is 750 hertz. Always helpful to just throw it into normal numbers and get rid of that extra mental step. One of them is stationary while the other police car is approaching Emma, who's standing on the curb, so presumably very close to the path of the car going past. Compare the pitch of the note that Emma hears to the pitch of the note the driver of the car hears as his car approaches. So the driver of the car will hear the pitch as it is. Emma is going to hear a higher pitch, higher frequency as the car approaches with its siren on. And the reason is the Doppler effect. They haven't asked us to explain that, but it's the whole bunching up of the waves as each successive wave is released closer to the previously released one, giving an apparent shortened wavelength. And then you've got your v equals f lambda for the same velocity. Apparent shortened wavelength means a higher frequency. Okay, B. The stationary car as well as the car approaching Emma sound their sirens. The frequency heard by Emma differs from the true actual frequency by 8.50 hertz. Show that the speed of the approaching police car is 3.81 meters per second. So 8.50 hertz is the original frequency, presuming the stationary car is playing exactly the same frequency. What have we got? So your Doppler equation, if depending on your notation, I can't remember what they do in the resource, but usually it's your f dash, your modified one, or f1, or however you want to put it, is your original f naught frequency, velocity of the wave over velocity of the wave plus or minus velocity of the source. We've got, that'll give us the modified frequency. So in this case, if modified, being the higher frequency, minus f naught, the original frequency, equals 8.50 hertz. And we have to show, combining these two equations, that the speed of the approaching police car is 3.81 meters per second. So that's the velocity of the source that we're trying to show here. So we know this, we don't know F1 and F0. But we do know the difference between F1 and F0, so we can then substitute one of those in, what else do we know? Cruise down a little bit here. Oh, we do know the identical sirens, so we know that F0 is 750 hertz. So we plug in 750 hertz into there and there, and then we rearrange for F1 and throw F1 into there and eliminate that, and then we've got F. So yeah, again, I mean, this bothers me a little bit about the type of question, because this is focusing more on a mathematical thing than a physics thing. And the maths of physics is important, but this is drifting a little bit from the concepts, if you ask me. I'd probably do similar things to try and come up with inventive new questions if I had to write an exam. I haven't written an exam. But yeah, anyway, Emma's standing very close to the side of the road as the police car approaches her and then goes past her at a constant speed. By calculating the apparent frequency of the sound Emma hears when the police car goes away from her, sketch a graph of frequency against position using the axes drawn above to show how the frequency... Was there an axis up here? Did I not see that? I don't know. There it is. No, drawn below. Anyway. Drawn above to show how the frequency... See, that's... Again, sorry, NCEA, sorry to the teacher who wrote this, or assuming you're a teacher. Little things like that can really confuse students. Above is not below, okay? Maybe I'm misreading that and I'm a little bit tired. Anyway, the frequencies show how the frequency of sound Emma hears changes as the police car approaches her from a distance and as the police car recedes from her into the distance. Note that they're not so interested in as the car passes directly. That's because depending on how close or far she stands from the point where the car passes her, you're going to have either a sharper drop off, a more instant, or a more kind of gradual decline. But we have to do a calculation anyway. So we want to find the f dash frequency. You've got to do two calculations actually. when it's going towards her, and then do the F dash frequency when it's going away. So we know F naught now. Oh, that was already given to us. We know the speed of the approaching police car. It was a show question, so we knew probably that they were going to get us to use that down here. We know the speed of sound in air. So V, velocity of the wave over velocity of the wave, plus or minus velocity of the source, and it's going to be the same for away. Excuse me, except you have to choose whether it's plus or minus. The way I always remember for plus or minus is if it's coming towards you, you know you're going to hear a higher pitch. Therefore, this portion has got to be greater than 1. So if that's going to be greater than 1, because you multiply F naught by a number, that increases it to F dash. So to make that bracket greater than 1, you have to have a number that subtracts from VW on the bottom, because then you have a smaller number on the bottom, which means a bigger number divided by a smaller number is going to be greater than 1. If it's the other way around, so on the bottom you're going to plus it, and that would mean you would have a larger number on the bottom compared to the top, for we're talking about down here, that's going to make the bracket part less than 1, so you're going to have the lower frequency. Less than 1 times a number means a number that's lower than what it was originally. Okay, so whatever that number is, you're going to have a straight line at the high point and then a straight line at the low point, and then you're going to have some sort of transition between the two. Yeah, they again haven't focused on, they've only focused on as it approaches and as it recedes. There could be some sort of marks to show that it's a slight gradual change. I mean, it can't be instant. There has to be a little bit of a change, and there's always going to be a slight distance away from the car as it passes. But it's not going to be instant in a perfect, in a real world. Okay, last one. Explain the reason for the shape of the graph you have drawn, and your answer comment on the shape of the graph. There we go. We've talked about all of that. On the gradient of the graph as the car with the siren approaches and goes past. So the gradient's 0 because it's effectively 0 anyway, because it's consistent. But then and it's 0 on both sides. And then depending how fast the car is going, it's going to be steeper or shallower. If it's a slower passing, it's going to be shallower because the change is less rapid. Gradient shows change. That's probably plenty to get you through and give you a sense if you've done okay at this or not. A few tricky bits there that kind of make you fumble a little bit. Yeah, well, hope you did all right and hope you enjoyed that and found that useful. Yeah, stay tuned for the other videos for 2022. Cheers. Oh, and just a little postscript. If you found any mistakes, feel free to bring them up in the comments. And it's it's always good to know. And I can edit the videos with a little bit of text overlay to include your suggestions. Yeah, be polite and respectful. But if you're not, if you've still got a bit of truth out there, I've got thick skin, and we should have thicker skin today than a lot of people do. So yeah, let me know if you think I got something wrong, drastically wrong. Much appreciated. Let's have a conversation. Cheers.